In this tutorial, we are going to talk about the ideal gas law and the Pascal's law. So what are these laws in fluid mechanics? Now, the ideal gas law is a result of combining three empirical equations, three gas equations that resulted in the ideal gas equation or ideal gas law, which says that the pressure is equal to the density, the R, which is the universal gas constant or the gas constant, and the temperature, the absolute temperature of the gas. So how did we obtain this ideal gas law? It was obtained from the Boyle's law, the Charles law, and the Avogadro's law. So let's get a look at this. From Boyle's law, we saw that it is volume of a given gas is inversely proportional to the pressure. That's for the Boyle's law. And for the Charles law, it states that the volume is proportional to temperature. Avogadro's law says volume is proportional to the number of what? Moles or molecules. Are we good? So combining the volume, which is a common term, combining all these parameters, can I say that the volume is proportional to temperature, the number of molecules, and inversely proportional to the pressure? Yes, I will have to introduce a constant, which is the R, which is the gas constant. It will differ for each gas. So I'll introduce the R as the constant. So R, T, N on the pressure. So if I cross multiply, it is going to give me N, R, T for the ideal gas equation. If I want to further deduce this, I will divide both sides by the volume, and this will be nRT on the volume. Therefore, the pressure will be equal to, because of the mole and the volume, I'm getting the density, the gas constant, and the T. Are we good? So this is the ideal gas equation. It helps us a lot in calculating for parameters of gases, where P is the absolute pressure, T is the absolute temperature, rho, this is the density of the gas, and R is a gas constant. And your R is different for every gas. So when I take CO2, CO, and maybe when I take hydrogen gas, the R will be different. The R for a gas is calculated as the Ru over the molar mass of the gas, where this Ru is the universal gas constant. It is a constant value. So you divide the molar mass of that particular gas to the universal gas constant, and you are getting the original R or the gas constant for that particular gas. Are we good? So this value is a constant value. The R is a constant value of the constant value for the R is giving us 8, or the Ru, the universal is 8.314 joule per mole dot Kelvin. So this is it for the universal gas constant. You can express it in kilojoule as well, and it will help you. So basically, this is the ideal gas law and how we obtain it. We will use it for many calculations in the upcoming sections. Let's get a look at the Pascal's law, one of the interesting laws in fluid mechanics, and it is practical. It helps us a lot. What does Pascal's law state? Pascal's law states that for a given closed system, remember the system should be a closed system, a pressure change produced at one point in the system will be transmitted throughout the entire system equally. Are we good? So let's take this as an example. This is a closed system. It is closed at the ends, and there's a fluid a fluid inside, let's say water or any oil. And if I change the pressure at the surface of, or I introduce a certain pressure at this end, that amount of pressure will be transmitted equally throughout the fluid. So the pressure here will be equal to the pressure at this point. Are we good? It will be equal to the pressure at this point. And with that, we can use it to do many other important stuff in the industry. Are we good? So it helps us a lot. Remember, once I apply a certain pressure here, pressure is force on what? Area. The force on area. So assuming I apply a 10 Newton force here, just a small force at this area, I will know the area. It will produce a certain amount of pressure. Let's say the area here is 2 meters square. Are we good? We are making an analysis, 2 meters square area. So from this, I'm going to introduce a 10 Newton over a 2 meter square. That's going to give me a 5 Newton meter square pressure. Are we good? So the pressure will be transmitted equally. So here is 5 Newton, here is 5 Newton, this place is also 5 Newton. And now a small force was introduced. Let's look at the output of the force here. Now we know that force will be pressure times the area. Since the pressure is constant 5 here, you just increase the area from this side. Let's say area of 2 or 20 meters square. And now, since the pressure is the same, I'm going to get a pressure of 5 times an area of what? 20. And you can imagine the amount of force it is going to what? Produce at this end. So this concept is very useful, and mostly it is applied in making the hydraulic lifts, hydraulic jacks, and brakes, which will meaning you have to apply a certain small force at a point, and the other point, since the pressure will be transmitted, the area is increased to produce a very large amount of force. Once the force here is increased, we can use it to lift other loads, and it's very important. So this is the Pascal's law. We will solve more examples and you'll see. Let's look at the fluid as a continuum. In fluid mechanics, this assumption is very important. We assume fluid to be what? Continuous, or the continuum assumption. The concept of continuum is the basis of classical fluid mechanics. In order to analyze fluids at any point in time, this assumption is the basics. Because of a body of fluid is comprises of molecules, we know for every fluid, let's assume this molecules of water, it contains what? Molecules. And the properties are due to the average molecular behavior. So the entire behavior of the fluid in this container is due to the individual what? Or the average molecular behavior. That is, a fluid usually, this is the continuum assumption. You have to pay attention. A fluid usually behaves as if it were comprises of continuous matter. That is infinitely divided or divided into smaller and smaller parts. This concept is called the continuum assumption. So what I want you to get here is that anytime we are going to consider a fluid, let's say an entire fluid, flowing or being static, we saw that the fluid mechanics, we have static and we have what? Those moving. Are we good? So if the fluid is in motion or static, we are going to assume that the particles are continuous. Are we good? Meaning at any point in the fluid, we can divide the molecule into smaller parts, and all these smaller parts combines to form the entire container or the entire fluid. And with this, if we consider any small part, since the fluid is continuous and the parameters are almost the same, we can make an assumption, we can do analysis at any smaller what portion. Are we good? When we get to the flow part, you see that as molecules of water are flowing, the Euler's principle and other principle, we can assume a target, or we assume one particle, and our analysis can be made from that particle, because we will assume that since it is continuous, the behavior of a particular particle is the same for all the particles. I hope you get the continuum assumptions. So we assume that all the particles are continuous, they are the same, and their properties are the same. So an assumption can be made by taking a small portion of the entire system. Are we good? So system and fluid properties. From the beginning of fluid mechanics, we saw that the properties of what the fluids will be discussed, and this will help us choose a particular fluid and to make our what analysis. First, what is a system? A system is divided or defined as a given quantity of matter. So anytime you are given a quantity of matter to study, it becomes what? Your system. Are we good? So I can consider this container as my what system. If I'm to make analysis of the fluid inside, this will become my system. If I'm to take the whole country and make some fluid analysis, it becomes what? My system of what? Study. The mass of a system is constant. We will explain that and we see why. Now let's look at the properties of a particular system. The properties related to the total mass of a system are called the extensive properties. Thus, they are usually represented in uppercase, example, mass, weight, and stuff. So the properties of a particular system are divided into two. We have what we call the extensive properties and the intensive properties. Pay attention to these properties. They are examinable. So the extensive properties are related to the total mass of the system. So they are dependent on the mass, while the intensive properties are independent on the amount of the fluid. What do we mean? Meaning, for the mass, if the mass of the system changes, the extensive properties are going to change. But for the intensive property, no matter the changes in the mass, then they are also not going to change. So let's make a drawing here and see something. So if I have, let's say this is a continuous container with fluid inside. So we have, let's say, a 10 kg amount of what? Water inside. With the extensive properties, example is the mass, the weight. If I take a portion of this fluid, remember this is the entire fluid. If I take a portion of this, the mass is going to change. The total mass is going to change, right? Yes. The weight is going to change because this will never be a 10 kg. This portion will never be a 10 kg. So this can either be a 2 kg, and it has changed the property. So if I want to measure the mass of this fluid, it will differ from the entire mass. The weight will also what? Differ. That's what we said. The extensive properties are dependent on the mass. But assuming that if I take this container to be a density of, let's say, 2 kilogram meter square, or a temperature of 60 Kelvin. No matter the amount I take from this fluid, the density is going to remain the same, the temperature is going to remain the same. If you have hot water and you take a portion of the hot water, that portion will contain the same amount of what? Heat as the total what? Heat. The temperature will be the same. So in order to get the understanding, the intensive properties are independent of the mass. If you take a small portion, the properties remain the same, and we have the pressure, the density, and the temperature. They do not depend on the mass. Are we good? So one property we will be talking about is the mass density, which is very common for fluids, for bodies, and for structures. So the mass density, which we refer to as density, this is defined as the mass per unit volume of a substance. The mass per unit volume of a substance. The density of some fluid is more easily changed than that of others with temperature. So some fluids changes their density with temperature, others also do not. And we saw from the episode 1 the studies of fluid mechanics, which there will be density change and others there will not be density change. So if you are given a system or a fluid, the mass density is the mass of the fluid divided by its volume. And this is the mass by its volume. Its unit is kilogram meter cube for the density, because volume is measured in meter cube and mass is in kilogram. So kilogram meter cube. Are we good? So water is considered to be incompressible because of the density change is very small over a large pressure. In the episode 1, we saw why water is what? Incompressible. We consider the molecular structure, and the density also will account for the reason. Are we good? So this is all about the mass density of a fluid. We can also consider another property which we call the specific weight. The weight per unit volume of a fluid or a substance is called the specific weight, and it is denoted by this gamma. Are we good? We said the gamma, which is the specific weight, is the weight per unit volume. We know that weight is also mass times what? Gravity over volume. Mass over volume from the first property we saw is density. So that will be density times this gravity. Are we good? So we can express the specific weight as the density of the substance and the gravity, or the weight per volume. Anyhow you express it depending on your question will be okay. Where g is the acceleration due to gravity, and we take it as 9.81 meter per second square. Specific weight has the unit of Newton meter cube. Remember, weight is measured in Newton and volume in meter cube, so Newton meter cube. One other property important to the study is specific gravity. It is also denoted by X, and it is the ratio of the specific weight of a given fluid to the specific weight of water at 4 degrees Celsius. Pay attention, at 4 degrees Celsius, because at 4 degrees Celsius water behaves what? Some way. The anonymous behavior of what? Water at 4 degrees. So we compare the weight of a fluid to that of, or the density of a fluid to that of water only at 4 degrees. So specific weight, let's say it is the specific weight which is, let's say specific weight A, gravity. The specific weight of A is weight of A and the volume of A. Are we good? Which is the same as we saw, it is rho of A then gravity. Then let's consider the specific gravity of B, which is the same as WB on volume of B. It is also rho BG. And okay, so let's assume we compare it to water, so the B should be for water. Are we good? Meaning the specific gravity X of that particular gas will be the rho A of that particular gas times the gravity, and that of the rho of water and the gravity. Remember, this gravity can take care, meaning specific gravity is always the gravity, or it's always the density of a fluid to that of the density of water at 4 degrees Celsius. It's very simple. We'll solve examples and you will see. We will also look at specific volume. These are all properties of a fluid. Pay attention because we'll be needing all of them. It is defined as the volume per unit mass of a substance. Volume per unit mass. So it is also denoted by the letter V, small v, which is specific volume. The volume per unit mass. Are we good? Remember, the density is mass per what? Volume. So can we say specific volume is the inverse of this density? Yes, which is the inverse of volume on mass. Are we good? Which will render us to mass on volume. So meaning specific volume is the inverse of 1 on the mass, or the inverse of the mass density. It is also measured with the unit meter per kilogram. Are we good? We are coming to the end of some of the parameters, and we'll continue with that in the episode 3. So let's talk about the specific heat, specific internal energy, and specific enthalpy. What do they mean? When we talk about the specific heat, is the amount of thermal energy or heat energy that must be transferred to a unit mass of a substance to raise its temperature by 1 degree. Because it is specific heat, we are talking about a specific heat, meaning we make analysis with reference to a unit mass. So for example, if I'm considering a unit 1 kilogram mass of water, how much heat can this water contain? That's the amount of the specific heat. So if I know the amount of heat a 1 kilogram water can contain, then I can do my proportion, ratio and proportion, to know the amount a large quantity can contain. So a unit mass of water or substance, by how much will its temperature be raised by 1 degree heat? Are we good? And the specific internal energy is also defined as the energy that a substance possesses due to the state of its molecular activity in the substance. So what the molecules are undergoing, the action they undergoing, the energy they hold inside the system becomes its specific internal energy. Remember, it is internal. The energy possessed by the what? The molecules. And the specific enthalpy refers to the total energy in a system due to pressure and temperature per unit mass in the system. So basically, these are 3 definitions of some properties of fluid. We'll talk about the other ones, elasticity, viscosity, in the 3rd episode. Thank you for watching. Subscribe to the channel.